Astronomers expect sky to be full of patterns, but sometimes one patch look quiet in a way that should not happen. The strange part was not that the space looked dark. Space is dark almost everywhere. The strange part was how sharply the stars seemed to stop. Astronomers do not search the sky by guesswork. They map it region by region, then compare one patch against the rest. That matters because the universe is not made mostly of things we can see directly. The visible part is only a small share of the whole. In astronomy, dark does not mean evil, and it does not mean empty. It means hidden from ordinary light. When something cannot be seen directly, scientists look for what it does. Motion can reveal what light cannot. One of the clearest places to test this idea is inside a galaxy where gravity shapes how stars move. If only the visible matter were there, stars near the edge should orbit more slowly than stars near the center. But when astronomers measured real galaxies, the outer stars were not slowing down enough. They were moving too fast. The simplest explanation was extra mass surrounding the galaxy, invisible to light, but real enough to add gravity. This became one of the strongest clues for dark matter. The motion inside galaxies was not matching the amount of visible matter they contained. The surprise was at the edge. Stars far from the center were still moving, as if much more gravity were holding them in place. Astronomers did not jump to a new invisible substance overnight. They reached that idea after repeated measurements kept pointing to the same mismatch. And it was not just one odd galaxy. The same basic pattern kept appearing again and again across many different systems. So the picture changed. A galaxy was no longer just its bright stars and gas. It seemed to sit inside a much larger halo of hidden mass. Then astronomers asked a bigger question. If hidden mass surrounds single galaxies, what happens when entire groups of galaxies gather together? The same problem appeared on a larger scale. In galaxy clusters, the visible matter still did not seem heavy enough to explain all the motion. By the visible mass alone, some of these galaxies should have escaped. Instead, the cluster held together as if extra gravity were filling the space between them. Rotation was one clue. Light gave astronomers another. Gravity can bend light itself, and that means hidden mass can reveal its presence without shining at all. This effect is called gravitational lensing. In simple terms, mass changes the path that light takes as it moves through space. When enough mass sits between us and distant source, even the background light begins to warp around it. That is the key idea. Light traces gravity so astronomers can map hidden mass by watching how background light gets distorted. In some cluster collisions, the visible hot gas slows down and piles up in the middle, but the strongest gravity appears somewhere else. That separation matters because it suggests the gravity is not coming only from the material we can see glowing in the middle. By this point, dark matter no longer looked like a few hidden clumps. It began to look more like a scaffold, helping organize where galaxies gather. And once astronomers started thinking bigger, the question changed again. What if hidden structure extends across the universe itself? On a larger scale, galaxies are not scattered at random. They gather along a giant cosmic web, with the dense intersections and enormous empty regions between them. This connection is stronger than we thought. The idea is simple. Galaxies tend to form and collect in the denser parts of the structure, where gravity has had more to work with over time. What we see may be only the bright trace of a much larger framework, with ordinary matter collecting along a deeper hidden pattern. By now, the evidence is strong that something unseen is shaping the universe. But what dark matter actually is remains one of the biggest open questions in science. Dark matter is only part of the story. There's another mystery, and it involves the universe itself getting larger over time. Since the Big Bang, space has been expanding. That does not mean galaxies are flying away from one spatial center. It means the space between large structures can stretch. For a long time, the expectations seemed simple. Gravity pulls matter together, so the expansion of the universe should gradually slow down. To test that idea, astronomers used distant exploding stars called supernovae. These events can act like cosmic measurement tools. But the measurements pointed to a shock. Instead of slowing down, the expansion of the universe appeared to be speeding up. That result was not a small adjustment. It suggested that something on the largest scales was pushing the universe apart more strongly over time. To describe this unknown driver of accelerating expansion, scientists gave it the name dark energy. But a name is not the same as an explanation. Dark energy is a label for the effect we observe, not a complete answer for what causes it. According to the best current picture, dark energy dominates the large-scale budget of the universe today. So here's the simplest contrast. Dark matter helps pull structures together. Dark energy appears to drive the expansion of space apart. Dark matter and dark energy already stretch our understanding, but some observations raise even more uncomfortable questions. One of the most important maps in cosmology is the cosmic microwave background, the faint afterglow of the early universe. Most of that map shows tiny variations, but one region appears unusually cold and unusually large compared with the rest. That does not automatically mean new physics, but it does stand out enough that scientists have spent years trying to explain it. So, what is it? A rare statistical fluke? The imprint of a huge cosmic void? Or a clue that something deeper is missing from the standard picture? The cold spot is not the only oddity. Some studies have suggested that certain large-scale patterns in the sky may look a little too aligned. If those alignments are real, then regions that should look independent may be showing a suspicious level of coordination. This is where science has to stay disciplined. An anomaly is not proof by itself. Sometimes a mystery points to new physics, and sometimes it fades with the better data. Another major tension appears in the expansion rate of the universe. Different methods of measuring it do not always agree. That is a puzzle in its simplest form. One method starts with nearby distances and builds outwards. Another starts with early universe. Both are powerful, and they do not land on exactly the same answer emission. So, what does the disagreement mean? It could point to hidden measurement problems, or it could mean our control model of the universe is still incomplete. Scientists have proposed many candidates for dark matter, including new kinds of particles that would interact very weakly with ordinary matter. For dark energy, the ideas range from energy built into empty space to changing cosmic fields, or even the possibility that gravity behaves differently on the largest scale. So far, none of these ideas has solved every problem. Dark universe is still a place of evidence, models, and unanswered questions. The way forward is not guesswork. Astronomers keep testing these mysteries with better sky surveys, better maps of hidden mass, and more precise measurements of cosmic history. With better data, patterns that once looked vague can become much clearer. That is how hidden structure slowly moves from suspicion to measurement. Put it all together, and the pattern is striking. Fast stars, bent light, accelerating expansion, and stubborn anomalies all point to a universe that is still hiding much of its true nature. The key idea is not that the universe is magic. It is that much of it has to be inferred indirectly from the effect it leaves behind. That may be the most humbling part of all. The ordinary matter we know could be only a small fraction of what reality really contains. The dark universe is not just a mystery in space. It is a reminder that the biggest parts of the cosmos may still be parts we understand least. If you are enjoying Curiosity Bin, like the video, subscribe, and hit the notification bell so you don't miss the next mystery.